All right, let's dive into the heart of the internal combustion engine. Inside every single one, there's a fire. But not all fires are created equal. You've got the perfect controlled burn that gives you all that power and efficiency, and then you've got its evil twin, a violent, destructive explosion that engineers literally spend their entire careers trying to stop. Today, we're getting into that story, this tale of two combustions.
It all starts with a sound, a sharp, metallic ping or knock when the engine's working hard. And for an engineer, that is one of the most terrifying sounds an engine can possibly make. It's not just some random noise. It's the sound of the engine literally tearing itself apart from the inside, thousands of times a minute.
And wow, this picture right here, this shows you exactly what happens. You're looking at a piston that was completely destroyed by that sound. This isn't just normal wear and tear, not even close. This is catastrophic failure, and it's all because the combustion went horribly, horribly wrong. It just goes to show you how critical it is to get this process exactly right.
Okay, so if we're going to figure out how to defeat this destructive villain, we first have to understand the hero of our story, the perfect normal combustion event. We've got to know what right looks like before we can even begin to understand what's going wrong. The best way to think about normal combustion is to picture the flame on your gas stove. It's a really, really fast burn, but it's totally controlled and stable. The key here is that a single flame, started by the spark plug, travels smoothly and predictably all the way across the chamber. It's a fast fire for sure, but it's not an explosion. So how do we even begin to analyze this? Well, we can actually use a framework from a guy named Sir Harry Ricardo. He's basically the father of modern engine research. He broke the whole thing down into 3 distinct stages, which gives us a kind of roadmap for what's happening inside that cylinder. And what's so cool about this diagram is that it's basically an EKG for the engine's heartbeat. It plots the pressure inside the cylinder against where the engine is in its rotation. So, you see point A? That's when the spark plug fires. From A to B, the pressure barely moves. That's stage 1, ignition lag. Then, boom, from B to C, the pressure just skyrockets as the flame spreads. That's your main event, flame propagation. And everything after point C, well, that's the cool down, or afterburning. So that first stage, ignition lag, it's unbelievably quick. We're talking like 2/10,000ths of a second. It's this little period of chemical prep work where the spark creates a tiny, stable flame that can start to grow on its own. It's short, yeah, but its length is absolutely critical because it tells the engine's computer how early it needs to fire that spark. And then we get to the main show, flame propagation. This is where that flame front expands out from the spark plug, just consuming all the air and fuel in its path. Now, the absolutely crucial thing here is timing. What engineers want is for the peak pressure, the biggest push from this burn, to happen about 5 to 10 degrees after the piston has reached its highest point. That's how you get the biggest, most efficient shove on that piston, which means more power. So that's the ideal. That's what we want to happen. But what happens when it all goes sideways? Let's get back to our villain, engine knock, and really dig into the mechanics of what's happening when that controlled burn just dissolves into chaos. Okay. This is super important. We've got to get a couple of terms straight because they're not the same thing. First, you have knock, which is also called auto-ignition. This is when the fuel and air that's way out ahead of the main flame front gets squeezed so hard and gets so hot that it just explodes on its own. Pre-ignition is different. That's when a hot spot in the cylinder, like a glowing piece of carbon, lights the fire before the spark plug even gets a chance to. And trust me, they often work together as a truly destructive team. And check this out, you can literally see the difference on this pressure graph. See the trace on the left? Nice and smooth, that's a healthy engine. But look at the center and the right. Those crazy, sharp, high-frequency spikes? That is the unmistakable signature of knock. Those are violent pressure waves, basically tiny shock waves slamming around inside the cylinder at the speed of sound. And those pressure waves, they are unbelievably destructive. We're talking pressures over 3,000 psi. They literally blast away the thin insulating layer of gas that normally protects the piston. When that happens, you get this massive spike in heat transfer, which leads to overheating, huge power loss, and eventually serious mechanical damage. It's a vicious cycle that can absolutely wreck an engine. And the physical evidence is just brutal. I mean, look at this. You can see the top of a piston that's been chewed up. It looks like it was sandblasted, but all of that damage was caused by the violent pressure waves from detonation. Here's another classic example. See that area right above the top piston ring? That's called the top ringland. And that kind of damage is a textbook sign of heavy, continuous knock. It's one of the first things an engineer is going to look for when they're diagnosing this kind of failure. And finally, you get the absolute worst case scenario. This is what happens when that nasty combination of pre-ignition and detonation is just left to run wild. The heat got so intense that it literally melted a hole straight through the piston. That is total catastrophic engine failure.
Okay, so after seeing all that damage, you're probably wondering, how on earth do engineers fight this? I mean, this force seems unstoppable. Well, they use a surprisingly powerful tool, and that tool is turbulence. They actually use controlled chaos to prevent uncontrolled chaos.
So let me just ask you this. Inside that cylinder, you've only got milliseconds to get this whole burn done. So how do you make a fire spread not just a little bit faster, but up to 50 times faster than it would on its own?
You wrinkle it. That's the secret. On the left, you've got a smooth, calm flame. On the right, a turbulent one. By churning up the air and fuel mixture, you get the flame front all wrinkled and distorted, which massively increases its surface area. And since the burn rate is all about surface area, the whole process just takes off.
And the numbers here are they're staggering. A totally calm flame might travel at about 1 meter per second. But by engineering the right kind of turbulence, that flame speed can get up over 30 meters per second. That incredible speed is the key to winning the race against knock. The flame burns up all the fuel before that leftover end gas even has a chance to think about exploding. So engineers have this toolkit, right? 3 main ways to get this life-saving turbulence. They can design the intake ports to create swirl, which is kind of like a little tornado inside the cylinder. Or they can create tumble, which is more like a barrel roll. And finally, they use squish. That's the high-speed jet of gas that gets squeezed from the edges as the piston comes right up to the top.
Okay, let's put it all together. When an engineer sits down to actually design one of these combustion chambers, what are the key levers they can pull to create that fast, stable, knock-resistant burn that they're looking for?
What's really fascinating about this is the incredible balancing act it reveals. Like, take a look at engine speed. You'd think faster means more knock, right? Nope. Increasing engine speed actually decreases the tendency to knock because there's just less time for anything bad to happen. But then look at engine size. Making the engine bigger increases the tendency to knock, mainly because the flame has farther to travel. It's a constant trade-off. And this all points to this really cool rule of thumb in engine design. Small engines, they run at really high RPM, but the flame doesn't have far to go. Large engines run at low RPM, but the flame has a much longer journey. The end result is that if the designs are similar, the amount of time it takes for the burn to finish, measured in degrees of crankshaft rotation, stays almost the same no matter the size. This lets engineers scale a good design up or down pretty effectively. And all of this leaves us with the big challenge for engine designers right now. We're all pushing for more and more efficiency. That means higher compression, running on less fuel, but those things make the flame itself harder to start and easier to put out. So the question becomes, how do we master this intricate dance of turbulence to control a flame that is more critical and yet more fragile than it has ever been before?